Okay, I'm going to record now. Okay, hi everybody. I am Victoria. I'm currently a fifth year at Pomona. I'm studying computer engineering. I joined Hyperloop with Chris back in 2020. And now I'm currently the VP here at CPP Hyperloop. And in regards to PCB design, I've been doing PCB design since I was around 15, 16. I started doing librarian work, which essentially is creating the components that PCB designers will use, working on library databases. Eventually there, I scaled to do more contracting work. And then from there, I started doing internships at SpaceX for PCB design. That experience is really great just because at SpaceX there's essentially a PCB design group that specifically designs flight hardware / test hardware. So that was a really great experience. And now currently I am a contractor for PCB design at Thermo Fisher. So have been in the PCB design space for a while now. So I hope I know my stuff well. I hope so. So yeah, that's a little about me. And so we wanted to introduce you guys to PCB design if you have been here or you haven't been here, just because I think or just in general in the industry, PCB design is pretty essential, especially if you're an electrical engineer. Especially, for example, in startups, PCB designers are a bit more niche, so that usually in the bigger companies, they'll have a PCB design group team specifically for PCB design, but in startups, they don't have that luxury. So usually all EEs do PCB design. So I think it's a good skill to have just in general, and it's quite fun. I think it kind of combines the difference of the technical aspect of engineering plus art. Also, if you want to quote unquote say business, because you do have to work with the EEs, the electrical engineers, the mechanical engineers, the manufacturing engineers. So you kind of get to touch a lot of different aspects of the project. So I think it's really fun. But yeah, so we'll just go straight into the workshop. I can't press the next slide. So.
Sorry, Vicky, do you want to screen share on your end?
Oh, okay.
Yeah, that was nice.
No worries. Slideshow. Okay, share my screen. Okay. Can everyone see it?
Yep.
Yeah. So we're going to go first into the intros to PCBs, and we're going to go about the why. Why do we even have to create a PCB? So in the past, as you see on the left, or just in general, if you guys are EEs or Comp Es, I'm sure you've seen a breadboard. I'm sure you've seen those little layouts they asked us to do to get a foundation on it. But essentially in the past, when they wanted to create bigger PC or greater circuits and greater circuitry, they'd have to design and assemble all these circuits through wires, through PCBs, and you can see it's very complicated. And today we have the technology to create electronically digital design of a circuit, which is very nice because even actually I did some research in today, like you would not be able to manually connect PCBs together or like we did in the past, just because our technology is so advanced at this point that we need this new development. So here's another reason. So this is kind of how in this picture an old Motorola television was formed. There actually isn't, it's basically just wood and everything was like connected via actual copper. And as you see, at least mechanical engineers and manufacturing engineers can kind of put it together in a box, but it wasn't that great. And then we moved on to holding the electronics through stamped copper onto the board, but still then it wasn't very great. And actually in this realm, when we started getting to manufacturing is when this first space race started between the US and Russia due to like the new electronics and new technology. So then we come to here where we have the next era of PCBs where we're able to design it, not great, still not using the best design for manufacturing guidelines. It's very new. So on the left is an old calculator. And I'm sure you can't imagine using something like that. That's the same size as today's motherboard. So this is where we are now. So going back to what is a PCB? So a PCB is an electronic assembly that uses copper conductors to create electronic electrical connectors between components. So you can see basically this is kind of a snippet of how a PCB is formed. You have copper, then copper is dipped into these little wires through our new technology, and then we can go through processing so that we can add those electronic connections on a PCB. This is kind of how it's made. This is a deeper end of PCB so that you understand, but this is how a PCB is formed. So you have copper layers on the top and the bottom, and you have some dielectrics in the middle to kind of help with any signal integrity. But yeah, those are big words. Don't worry about it. So different types of PCBs. We have rigid PCBs, which is usually the ones that you will see. This is not a rigid. I'll talk more about this picture soon. But you have a single-sided PCB, which essentially is a PCB, and the components are only on one side, and usually the bottom is ground. For people that are more interested in electrical end of it, you know that you need ground to kind of help with that signal integrity, because there's relativity to those signals. Double-sided means that there's components on both the top and the bottom. The multi-layer PCBs, like, they can scale up to around 32 layers, which is really rough, but that's kind of like, it depends on your manufacturer if they can even handle that. And then a rigid flex PCB is something that is connected via polyimide ribbon. So as you can see in the picture on the right, you have all these, they're considered rigid flex PCBs because they're connecting over to each other. But if we pretend that none of the ribbon is there, these are essentially their own rigid PCBs, but not. That's controversial. Basically, yeah. So the structure and applications of PCBs. So this is what we're going to talk about more, which is a layer stack up, which is built with alternating layers of conductive insulating material. So as you can see, like I said, there's copper, there's prepeg in the middle, which is a dielectric. A core is also another version of a dielectric, which helps insulate the signals, helps with signal integrity, whatnot. But this is, for example, a 4-layered board. 4-layered meaning all these copper. Yes, layers 1 to 4. Oh, never mind. Let's just skip that. I cannot think right now. Okay, so terminology. We're going to go straight into it. And just a preface for everybody, this is going to be an information overload. I don't know if Chris told you that already, but the point is that when you get to these sections and when you get to these kind of topics, whether that be in your jobs, in class, in whatever form, you'll have some sort of indication of what they're talking about. Then you can kind of probe more into those conversations. But this is going to just dump all that information in. So the PCB component architecture, essentially a component in a 2D form that's getting built on a PCB is comprised of 3 different schemas. So essentially there's a schematic and a symbol. So if you're in EE, usually you're working with the schematic, so you'll see like the schematic symbol. So essentially over here, for example, we'll see like schematic. This is in the schematic with the circuit. This is a symbol inside the schematic, and it's mapped to a footprint, which you see exist on the PCB dock, which we're going to talk later about. And then this is what a PCB is. So so basically, we're going to go from a schematic to a PCB, because the form factor is that you have someone create a circuit, but they don't have a physicality to it. So you want to create something that can be printable. And then also there's a 3D step model that is a part of this, which is the 3D layout of the component, for example, in real life, what it would look like, the dimensioning, whatnot. So this gives us connectivity. So a pad, essentially is an exposed region of metal on a circuit board that the component lead is soldered to. So these little copper areas are called pads. Pads are also in vias. It's anything that is exposed copper on the circuit that you probably have seen a lot and that you see soldered onto a lot, or you solder that metal onto the board a lot. So that's a pad. A through hole versus surface mount. So in the past, we used through holes a lot, just because we didn't have the technology to have surface mounts. But essentially, through holes, like you see the hole going through the board. And then a surface mount is that it's soldered on top of the board, nothing going through the board, but it still creates a connectivity. A via is a hole that goes through the board, and there's different kinds of vias, and it's electrically connected by copper as well. So as you can see down here, these are all vias. All the holes are little vias Then there's different kinds of vias where it's just a whole hole going through the entire board. There's something that's not plated, so it's not actually connected via copper. So for example, you'll think of that when, for example, if you're a mechanical engineer, you'll see a not plated hole for attaching the PCB to a chassis, right? You don't really need connectivity. You just need to make sure the PCB is held in place when they're doing testing, like thermal testing, vibe testing, anything. Then you have a blind via that kind of goes midway through the board, a buried that's inside, and then other types. These are, don't worry about these guys too much. I'm just giving a idea of what it looks like. But yeah, so essentially also as you get higher into different types of vias, the more difficult it is to manufacture as well. So if you're a manufacturing engineer, it would be a great topic to look into. A track is a line or conductive path of copper that runs all over the circuit board. And this also doesn't mean it's only on the top layer, right? So when I was saying a single-sided versus bottom or two-sided or multi-layer, there's multiple layers that can have copper, which means that there needs to be connectivity, right? So for example, over here, like you see on the silk screen or on the PCB, you see like this trace visibly, and this is on the top layer. But you don't know if there's anything in the middle, right? So for example, this is when it gets crazy. This is called DDR, tracing, routing. So every single color is an assumption because maybe they didn't change preferences. But the point is that every single color is a different layer. So essentially, creating a PCB is basically, in its purest form, I'd like to say, making a puzzle without knowing what the end puzzle looks like. Because you have to know how to really utilize every single layer with its requirements and with making sure that it can actually work when it's printed out. So nets, oh my God, I can't talk. A rat's nest or a nets are basically lines that are formed on a 2D version that show you the electrical connectivity between certain signals. So over here, this is our simple Hyperloop layout. But essentially, like, so this pin enters over to this pin enters over to this pin. It can get as crazy as something like this, even crazier when you have hundreds of millions of components on the board. So yeah. A silk screen is the ink traces that are on the board that designate any reference. So for example, like this is, or any of these components can say like this is P29, P28. This is helpful for electrical engineers. And it just showcases the logos and any marks on the board. A polygon pore is a copper pore that is attached throughout the entire layer. And this is something that you can also define what signal it is. So for example, a lot of electrical engineers will want ground everywhere so that they can ground all their signals and have a return path, a relative path with that signal. And it helps a lot with a lot of electrical magnetic shielding, RF shielding, any of that fun stuff. A DRC check is a design rule check, and I hope I didn't lose you guys here. I can't see you guys, but I hope you didn't lose you guys. But a DRC check essentially is when the manufacturing engineers have built, and this is also a standard within engineering, hardware engineering in general, is that DFM, design for manufacturing, will say that with this kind of creation, you have to make sure that these guidelines are met and that all of the PCB design is accurate and that we are able to it will be electrically functionable when it's created. Because that's the point of a good PCB designer, is that you can hit it, you can create the PCB design on the first run. That's when you're a good PCB designer, is that you know how to follow the rules, you know how to create a good PCB. Because then if you're thinking from a business standpoint, you mess up one PCB and it costs what? Usually the first PCB is maybe a couple thousand, if depending on the project that you're building. But if you can really create a good PCB, then you're pretty set. And so you just follow the design rule check. So we're going to go into starting a new PCB board design. And I'm going to pause. Does anyone have any questions?
All right. Does anyone have any questions right now they'd like to ask Vicky? Raise your hand. You've got no questions so far.
Cool. Okay, so now we're basically going to go through PCB creation workflow. And so this is the idea of how does a project get formed? How does an industry, an electrical hardware project even get built? So usually there's front-end engineering, which is a circuit design, mechanical development. So essentially, if we're thinking something relatable on your phone, right? So the phone needs to have some IC unit inside that can allow the board or allow the phone to function. So the electrical engineers will come in, will create the circuit, then they're like, well, we have requirements that the phone needs to be this dimension, which comes from mechanical engineers, also the client, whoever's creating it, they'll come in, and the manufacturing engineers, are saying, well, with this project, what grade will we be able to cover under, because the more difficult it is to process and to create, the more money the company spends. So this is the front-end engineering. So the circuit design is made, mechanical chassis is developed, then manufacturing engineers come in. Then, when everything's approved, electrical engineers will come with schematic capture, and then they'll show, for example, in Altium, they'll create the schematic layout. Manufacturing engineers will choose the material and PCB stack-up design to mitigate, for example, costs, whatever it means. And then from there, we're like, well, we have to create it into some physical form. So we go through component placement, routing, design review, verification. Design review and verification are basically done by every single person to make sure that everyone's following what they want to create and that they are able to create it. And then we ship it over to manufacturing. Then after that, it's gone through testing to make sure it is viable. But in this instance of a PCB designer, there's a different workflow because we're narrowing in on our work, which essentially the first point is that now that we have the mechanical engineers and the manufacturing engineers saying, it's a go, we're going to create this shape, this is how we want it, then you're going to define the board shape on a 2D form, which is what PCB layout is. And then you're going to define the placement, which is up to you, as long as you grab all the electronics that the electrical engineer says to put on through their schematics. And then you'll verify it with the electrical engineer to make sure that, like, for example, electrical engineers will say, no, we want the header on the top right side, and we want a hole in the middle for what reason. So it's basically verifying through a bunch of different layers of people to make sure that we are fitting to what they want, but we also have the flexibility because we're creating the 2D form of it. Then we'll go into routing. So that'll be like vias and polygon pores I was talking about earlier. So this is just like our own creativity. Then we'll go through the silk screen, designing whatever, whatnot. I don't know if you all have been to the current or the previous workshops, but for example, Chris has his little Ohm logo on there. That's also called silk screen, and you can kind of design whatever. It gets really fun if your company allows it to, or if you want to create your own free game. Then we'll go through DRC, and then we'll go through documentation. So from here, I'm going to leave it to Chris to go over the challenge for today, and he's going to show us a circuit.
All right, thanks, Vicky. That was an awesome presentation. Let me just in now. Cool. All right, I think I gotta go ahead and switch the screen now. Apologize, guys. We never had to actually do this before, where we have a hybrid kind of workshop, but I'm super glad that Vicky was able to make it today and be a part of this experience. So let me go ahead and just put it back to section 4. All right, so everyone on Zoom can see the current slide, correct? You gotta go ahead and move this here too. Oh. All right. It's weird because you get to see the recording's not hitting me. So, okay. I think we've transitioned correctly. So, as Vicky has previously said, PCB design is kind of like a combination of electrical engineering and a little bit of manufacturing engineering and a little bit of puzzle design too, because eventually you've got to connect all these little traces together from the board and kind of make this cool little diagram, cool little design. So me, as the electrical engineer, and I am going to give you guys a circuit to design me for. How many of you guys here have worked with 7-segment displays in your career or in some classes? Raise your hands. So a lot of you. Cool. And if you've ever worked with a 7-segment display and you've worked with it on a breadboard, you will know that it's a pain in the butt to connect because one of these little 7-segment displays has almost 10 terminals. Actually, it is actually 10 terminals, 8 terminals. So 7-second displays require a lot of wires to connect, and it's often very annoying if you want to do something like this, where you put resistors between each of the switches and the display. A 7-second display is made out of 7 LEDs, or 8 LEDs if you want to count the decimal points. Each LED is formed in such a way that lighting up certain LEDs creates certain patterns that resemble numbers. So for example, if I light up certain of these LEDs, I can make numbers from 0 to 9, or you can make letters from A through F, right? Usually this is how we represent a hexadecimal number code instead of a 7-segment display. So I think that's pretty cool. Now, because it's so painful to actually like connect things to 7-segment displays all the time, if you've taken a class like 2300 in electrical engineering or 3301, you'll know what I'm talking about. It'll be much, much easier if we could just take one of these little chips and put it onto a PCB that already has everything connected to it. The most common circuit that you would use this 7-second display for is a 4-bit decoder, or you put in 4 bits into this PCB and it gives you a number as an output. And we're looking at the black box problem like that. So when we're designing this PCB based on the circuit that I'm going to give you, we can think about this problem in 4 different steps. The first step is to look at what's called a decoder module. So the question is, how do we get our 4-bit input, which is represented by the 01 to 04 symbol here, into the 7-bit output, or like whatever we see on the 7-segment display, right? In order for us to do that, we have to use a decoder, a 7-segment to, or a 4-bit binary to 7-segment decoder. And this chip is known as the 74LS47. The purpose of this chip is to take a 4-bit number and to output a combination of signals, which represents numbers on a 7-segment display. Now, this specific chip is for a common anode 7-segment display. And there's a difference between a common anode and a common cathode. Now, you'll notice here that this 7-segment display has a ground, a common ground. Now, this is known as a common cathode. However, an alternative version of these displays is called a common anode. You'll usually see it represented using a CA. The common anode display has all of the pins connected together into 5 volts, right? Into VCC, voltage common collector. So that means in order to power on an LED and to complete the circuit, my input will need to be a ground, or a 0, or a low, or a false, or any of the other digital logic terms we covered in the past workshops. So again, the purpose of the circuit, take 4 bits of an input and then give us an output representing all of the 7 segments in the display. And these will be numbers from 0 to 9. You can represent letters A through F. That would be a binary to hexadecimal decoder 7-segment display. I think those chips are a little bit deprecated. This chip model right here, this chip footprint actually, is a chip that has been made since like the 1980s and 1960s. Now, they wouldn't make these chips anymore if students don't use them anymore. And we actually use these to teach, digital logic, right? You use these in your 2300 classes or, like regular lab classes to see how these displays work in the first place. So that's why we still use them today. But, these dual inline packages are growing rarer and rarer as the days go by. You'll notice that this chip also has some 5-volt and ground. This is like external power. Almost all chips need this in order to power them up. And you have LTBI, RBI. These are like the reset and clear pins. We connect them to 5 volts just so that they don't, reset our 7-segment display. So this is the first part of our circuit. It's kind of like the brains of our circuit. This is the smartest part of our circuit that tells the 7-segment display what number to show based on our input, right? If we're looking at this like it's a black box problem, we have our input, which is a 4-bit number, and our output, which is a 7-segment display. Does that make sense to everyone? Cool. Second part of our circuit is user input. Now, user input modules are important, at least in this form of a PCB, because us as the users, or whoever you're giving this to, needs to be able to, interact with the 7-segment display. They need to input a 4-bit number. The easiest way for us to input some number like this is to use a bunch of switches, right? Switches are cool because users can play with them. They're like something physical, and they allow the user to put in any number they want. Now, if we talked about switches in the previous circuit analysis workshop and the circuit construction workshop, and you'll notice that it's a little bit of a configuration here. It looks like an array. If we take a look at only the switch 1, you'll notice that output 1 is connected directly to it, right? If switch 1 is connected between the 1 and 2 terminals, then 5 volts will get sent to the output. And this indicates that we have an output of 1 or true, right? But we can also see here that there is a node connected to the end of output 1, connecting it to a resistor to ground. Does anyone know why we do this? This is a pull down resistor. Who said that? Awesome, great job. Yeah, exactly. So these resistors down here are called pull down resistors. The purpose of these is to pull down the signal such that if the switch is turned off, the output will receive a ground signal or a 0 signal, right? If we don't have this, then the output will be confused as to whether our input is a 0 or a 1, right? Because if nothing is connected to it, right? If this wasn't connected to it and the switch is turned off, then this would be a floating wire. We wouldn't exactly know what this wire goes to, which is why if the switch is connected between the 2 and 3 terminals, which means in the off position, then this signal from ground will get pulled. Well, this will pull it down to ground, but the output will read a 0 signal, telling the chip that you're putting in a binary number of 0 into that bit. That makes sense for everyone? We just repeat that 4 times and make it look cool like this. So again, the purpose of the circuit is to allow a user to choose a 4-bit number for our circuit. Okay. Now, I like to call this a user validation module. Whenever we build a PCB, it's really important for us to, confirm with the user that they know what's going to be or what they've done to the PCB, right? If you're building and testing the PCB and you're flicking on and off the switches, you kind of want to know that they work, right? So in this case, all the circuit is connecting the outputs or what the user puts into the circuit and connecting it to an LED to ground. Because, when we build a PCB, we want to make sure that when the user flicks a switch, it works. And the easiest way to do that is to have a visual indicator of the thing working. So here we're going to put a bunch of LEDs on each bit to indicate that, yes, the user has turned on the bit, and yes, it is working correctly. And our last module is kind of like the more complicated module. If you're an electrical engineer, this is for you. If you're a computer engineer, you also got to know this, but this might not be as interesting. Now, in every PCB, even if you're working in digital logic, even if you're working with Arduino, even if you're working with microcontrollers and that sort of logic, you need power, because without power, you can't power on the PCB. It's just not even there. So this module is for providing the circuit with power. Whenever you're dealing with power in a circuit, you have to ask yourself, how much power will my circuit need, right? In our case, we're powering a 74LS47 chip and a 7-segment display, which utilizes 5-volt TTL. Does anyone know what TTL stands for? Transistor to transistor logic, correct. So this is kind of like the logic that most microcontrollers use. They also use 3.3-volt transistor logic for some microcontrollers, but in our case, we only use 5 volts, which means our circuit will need 5 volts of voltage, and we need to find a way to provide it that. Now, the second question to ask is how much current will our circuit draw? If we put in the 5 volts to our 7-segment decoder circuit, how much current will it draw? Don't know? There's not one answer. It's about, give or take, like anywhere from 20 milliamps to 100 milliamps, right? The most power consuming object in our circuit is, anyone know? It's kind of something you got to identify, because that's going to become a problem for you when you design a circuit, in which Vicky will probably tell you about later, IPC. Yes. That's a good guess. It's not the decoder, though. Decoders, or anything that uses logic, usually has low-level signals. So it wouldn't be anything that deals with logic, but it's a good guess. Anyone else? The logic gates? Again, anything with logic does take fairly little amount of current. If you look at the data sheet again, it deals with anywhere between 4.5 milliamps and like 10 milliamps per se. Not very much of a concern for us. There's one component in there that's a very big concern when dealing with current. Not the capacitors, not in this circuit, the whole circuit. So everything we've talked about so far too. Who said that? 7-segment display? You're correct. So whenever you're dealing with a circuit, if you're using motors, if you're using LEDs, if you're using lights, anything that's an output usually draws a lot of current. This thing, each LED inside of this glows brightly. And in order for LEDs to glow brightly, they need current, like lots of current compared to just like small level logic signals. This draws anywhere between 20 milliamps to 100 milliamps. If you're using those like LED strips that you use to decorate your room, those draw a lot of current. You can average about, basically say that each LED inside this that lights up draws around 20 milliamps of current. So if you have 7, that's almost like 140 milliamps, right? That's quite a lot of current. If you just think about that, like 1 amp is enough to kill you. That's like 1 amp is a lot of current in the electrical world. So even a tenth of that residing on just this one component right here is a very serious thing, right? So we've identified that the 7-segment display will draw a crap ton of current. So later on, when you design a PCB, just keep that in mind. Anyways, that doesn't really matter for us. We know our limitations now. Pretty much our circuit is going to draw 5 volts and what did they say? Like 100 milliamps of current. So we got to make sure that our regulation module can support that, or whatever power we provide to the circuit will support that. Now, there's a lot of different types of things you can do to provide a circuit with power, right? You can use a 9-volt battery. You can use an 18650 cell. You can plug it into your computer. You can plug it into the wall, right? A lot of different ways to power your circuit. In our case, I'm going to use a 9-volt battery because a 9-volt battery can supply my circuit with 9 volts. You know, that's a little high for 5 volts, but I can push that back down with a regulator chip, right? And 9-volt batteries also provide, or you can draw about 0.61 amps of current from it. That's kind of like maximum. So you can't use a 9-volt battery to power a giant motor, right? Because a motor will draw like anywhere from 2 to 3 amps. But 9-volt batteries are great for just like small experiments like this. And it also accounts for our current limitation of 100 milliamps. So 9-volt battery is good. You can also use an 18650, right? An 18650 is a type of battery that is 3.7 to 4.2 volts when it's charged, and it can discharge a lot of current. I use some 18650 cells that discharge about 20 amps. That's like 20 times the amount of a 9-volt battery, right? So you can also use that to, power on your circuit. But in this case, I'll just use a 9-volt battery. Now, the problem with using a 9-volt battery is because, well, in its name, it's a 9-volt battery. Our circuit can only handle 5 volts. If you plug a 9-volt source into a chip, there is a chance that it might explode. And in circuitry and electronics, that's bad, right? If you never exploded something before in like one of your like labs or circuits or projects, you'll eventually will. But it's okay because you're learning. Anyways, 9-volt batteries, right? We can use a 9-volt battery to supply our circuit, but the problem is we'll need some way of regulating that. And this chip right here, the AMS117, is a perfect solution for this. Does anyone know when we talked about this sort of like regulator in 4x02 or the circuit analysis workshop, like what does this do? Anyone? Yeah, it regulates the voltage. It's as simple as that. It takes in a voltage higher than 5 volts and it spits out a voltage equivalent to 5 volts. That's basically it, right? Pretty simple. And this is an S&D component, which stands for surface mount device. So this chip is like really tiny, but not tiny enough so you can hand solder it. So we have this chip, which takes our 9 volts, turns into 5 volts. Great. Why are there like so many other things here, right? Your electrical engineer, when you're designing your PCB, usually will have a whole bunch of other stuff. You can ask him, like what the stuff is. Some things are going to be like really by default. These capacitors are here. Actually, I'm not going to answer that yet. Does anyone know why these capacitors are here for this chip? Will it? Elimination of noise. Yes, correct, right? This chip inside of it has a bunch of transistors, and transistors really like dealing with flat signals or like really clean signals of voltage. You don't want voltage coming to this chip that looks like it just had an earthquake, right? Or a seizure. Like voltage that's shaky and like varying is really, really bad. So capacitors are used to deal with that, right? We have 10 microfarad capacitors here to deal with large noise, and then 0.1 microfarad capacitors here to deal with small noise. And we have them on both sides because we're assuming that the voltage going into the chip is going to be noisy and the voltage coming out of the chip is going to be noisy, right? That's why these capacitors are here. Okay, great. So now we know why this chip needs to be here and why these 4 capacitors need to be here. What's with everything else, right? So this circuit up here, does anyone know what it is? Well, it's a diode, but it's an LED, yeah. So what's its purpose? Light? Anyone say light? Yeah, it just lights up, right? Again, in the previous slide, I talked about user validation, right? Making sure the user knows what's going on in the PCB. Also really, really helpful when you order and design your PCB to make sure you have stuff like this going on your board, because it's good for troubleshooting. It basically tells me that, okay, my circuit is giving it power, right? So I know at least if something goes wrong and a component blows up, it's not this part of the circuit because the LED light up, right? This is the most simple circuit. You're giving it some voltage, in this case it's 9 volts. You're putting it into the LED, putting it through a resistor, so you don't short circuit it, and into ground. So again, user validation. You're telling the user that, you know, your circuit works. Great. Everything to the right of this diode, we know what's going on, right? Keep going. This diode, D5, 1N4001. What the heck is going on with that? Why do we need that thing? Anyone? Yes, so diodes will allow current to flow in one direction. What will the diode not allow it to do? Current can't come through the other side, right? Good. So why is this diode there? To protect the rest of the circuit from user doing stupid things, right? And not just the user, yourself might do the stupid thing of connecting the battery backwards. So through this terminal block here, if you connect the battery backwards accidentally, and you don't have this diode here, current's going to flow backwards through the wrong direction into this chip and blow it up. If you've never watched AMS explode, it's kind of like a cute puff of smoke. And then your hopes and dreams will go away until you resolder another one. So in order for you to not have to go through that mess of, you know, like checking your circuit and fixing it and whatnot, you can put a diode there. Now, in the previous workshop, we also talked about the downsides of diodes. What's bad about a diode for reverse polarity protection? Anyone?
Oh, it takes like 0.7 volts?
Yeah, so it steals voltage. In order for the diode to be powered up, it has a voltage drop of around 0.7, right? So if you measure the voltage across the diode, it's usually around 0.7. But that 0.7 also takes away from the rest of your circuit. So at this point, at this node right here, you don't have 9 volts, you have about 8.3 volts, right? Now in our situation, because we're regulating down from 9 volts to 5 volts, we don't need anything in between. That's okay for us, right? But again, if you're using something that's very low voltage, like 3.3 volts, you're going to want a different solution than that for reverse polarity protection. And one of the solutions you can use is use a PMOS, which is a metal oxide semiconductor device. But we're not going to be talking about that today. You can go back to 4x02 and think about that or learn about that later. Great. So now we know what this part is. Let's move on. What's this switch here for? Anyone know? Yeah, exactly. Right? Because when you build your circuit, and you're going to want this because you're going to be using your circuit a lot, you want a way to turn your circuit on and off, right? Because that will allow you to reuse your circuit over and over again without having to disconnect the battery. So again, a lot of things in this circuit right here, although the main goal is to regulate the power from 9 volts to 5 volts, a cool thing about it is that it also has a lot of utility, right? I love putting utility in my circuit. It's like extra features or quality of life updates to your circuit that will help you in the long run when you use it. Okay, so just to summarize, we have 4 modules in our circuit. First module being the brains of the circuit. The decoder module turns the 4-bit number into a 7-second display picture. The next one is the user input, allows the user to play with switches in order to get the outputs, and also, your pull-down resistors right here. Next is user validation. We talked about user validation, how you can validate that the user's inputs are correct. In this case, we just put in LEDs. And finally, power regulation. We need to give the circuit power. We need to give the circuit the right power. So we need to understand exactly what are the maximums of our circuit in both voltage and current, and then design for it. Okay, Vicky, back to you.
Do you want me to share screen? Hello?
Yep.
Oh, okay. All right. Well, wait. Oh, I'm sharing screen. Okay. Sorry. Okay. Well, before we split off, we're going to talk about the challenge. So Chris kind of went over all the aspects of the circuit. He's your EE for today. and he's told you other requirements, right? How much current it is, how much voltage it is, the certain components to kind of look at, and that's more so that's something you'll have to learn over time. Essentially, those are the requirements that he's talking about. And for example, in a different PCB layout, higher level design, like in industry, they'll talk more about like board design, where that board is specifically fitting into, what's the point of the board. These are the requirements that you have to follow, especially if you're a PCB designer. So the challenge is to create the project. So that means right now, because this is a practice workshop, you're going to be designing your own schematic document as well as designing your own PCB layout. If you know anything about BOM, or the bill of materials, essentially is the materials that are being put into the PCB. In a higher form factor in industry, they'll talk more about like the cost, the quantity, blah, blah, blah. But this is basically just a list of the components that we're going to be using. I also broke it down for Altium users to look into these certain libraries. But yeah, so I'm just going to let everyone swap. So whoever's doing Altium Designer, stay in this room, and whoever's doing KiCAD, go with Chris.
All right, before we do that, let me go ahead and just say a few words first. This is probably going to be the last time we are in this room, or at least together before we split off. So I just want to go ahead and talk about the post-workshop activity. So from this point on, whether you're doing Altium or KiCAD, you're going to be designing the same circuit. You're going to be designing the same circuit schematic, putting it onto a PCB, arranging it in some sort of layouts, and getting the Gerber files and having the PCB designed. All right. So this is our encouragement for you to be able to design your own PCB after the workshop. You have 2 weeks after the workshop, if you check the box yes in the registration, to make your own PCB, right? You can make the same one as ours and personalize it by making it your own name, logo on the silk screen, whatever. Or you can do it yourself. You can find a problem, like maybe like you want to make a circuit with Arduino, for example, or you want to make a circuit to power a motor, like an H-bridge, for example, right? Possibilities are endless. But if you make your own PCB and you send us the Gerber file, we'll order it for you for free. And we'll deliver it to you by the soldering workshop, which is on March 24th. So you have about 2 weeks to complete this. And after the 2 weeks, we won't be accepting any more because we have to order them for shipping. But if you send it to us on Discord for the next 2 weeks, we'll be able to accept that. Right? Before we swap, are there any questions as to anything we've said during this first hour? Everything was crystal clear. Yes.
LEDs for each individual switch.
Mm-hmm.
Those will also be taking voltage away from the circuit, so they need to be accounted for.
It will be taking current away from the circuit, right? But they'll be using the same voltage as whatever node is before it. So you can think of like each component in your circuit as using some amount of current, like taking like candy away from baby, and baby being the power source. But you do have to consider that, but it's not too big of a consideration. You can just calculate it afterwards. But you are correct, they do take current. Any other questions? Okay. So for right now, raise your hands if you're doing KiCAD. Okay. Put your hands down. Raise your hands if you don't have if you don't have Altium or KiCAD installed. Oh, you can renew it really quickly. Okay. Okay. The recording will be posted afterwards, so you can follow along. Anyone else not have Altium or KiCAD? Okay, if you don't have Altium or KiCAD, you're going down KiCAD. It's faster. So just go to KiCAD's website right now. You can just click download, and then you'll follow me to the next room. So if you are doing KiCAD for the workshop, go ahead and begin packing up, and meet me in the next room. We'll go over the circuit. All right. For the rest of you, Vicky will be guiding you through Altium, and actually, for KiCAD, just go ahead and pack up and leave first, and then I'll discuss the rest. Oh, just go to the student license webpage again, and then register for it again. So Altium student 5. Okay. All right. For those of you who are remaining, everyone here is Altium, right? Okay. So if you are in Altium, unfortunately, Vicky isn't here, Sam isn't here to help you guys out, but we do have some helpers who know how this stuff works. So if you need help at any time during this next hour, you will be going to or asking for help from the following students. Addie, you can stand up and introduce yourself. Okay, so Addie, Yash, and Zach. Okay. Okay, so if you need help, go to them. Otherwise, Vicky, you can take it away.
Okay.
Sorry, I messed up. If you're in high school and on Zoom, I almost forgot the Zoom people. You can, if you're in high school, you can finish Altium because it's not real, but you are going to be going in a breakout room with me. So I believe I'll just open the breakout room. If you can join it and use KiCAD, we'll be in the next room. All right. Have fun, Vicky.
Thanks.
Okay. Now, I've never done a recording in which I've switched from one room to another. Usually it's like a separate thing, but I'm just gonna hope the recording integrity stays, and so we can complete this side of the workshop. Okay. So, you guys have KiCAD 7.0 open. I'd just like to talk about a little bit of the history behind KiCAD. The 7.0 is like its version number. Before KiCAD 5, the library manager was a little bit hard to use. The library manager in general for any EDA program is where you get your footprints, symbols, and other components from, and 3D models. Past KiCAD 5.0, the library manager became easier to use. By default in KiCAD, you're provided with 50,000 of the most common electronic components to use. Because when you're dealing with PCB design, one of the most difficult things you'll ever come across is searching for the right footprint or symbol that goes with the component you want. Because if you're using something like an IC chip, sometimes that just won't exist already. Someone has not made the symbol or the footprint associated with that chip. If you're doing something like the ATmega328P, which is like an Arduino, that's very, very common. But if you're doing something really like intricate like an MCU or like an MPU 0050, which is an inertial measurement unit, sometimes that won't exist yet. So there are a lot of teams of people around the world, and their entire job is just to take electronic chips, like new ones off the shelf, and make footprints for them. It's an actual job. You know, if you want to go and do that, sure. I feel like that's like kind of like the boring part of PCB design. What we're going to do now is we're going to go ahead and get started with our PCB. So go to File and select New Project. And under New Project, you can go ahead and create your new project under a folder. I have a folder under my documents called KiCAD 7.0, but you can create yours in another one if you wish. I'm going to name this 4x04 for the name of the workshop. And it's going to be the SSD, which stands for 7-segment display decoder. All right. Now you'll notice when you create a new PCB design, you'll automatically get both a schematic, which is the bottom one, and you'll also get the PCB schematic, which is the top one. They're both called schematics, but one's for symbols and one's for actual footprints. Go ahead and click on the the circuit schematic, which is the one right here. Now, if you went ahead and followed the guide, you can have like custom colors. I like dark mode, so I use W dark, which is the best theme in my opinion. But if you don't have that, it's okay. You use the light mode if you want, or you can go to preferences and select your color theme as you wish. Now, the first module that we're going to do, does anyone remember what the first module is that we talked about today? Yeah. Yes, so we are going to be using the 7-segment display and the 7-segment decoder and creating the logic that turns our 4 bits into the pattern that we see on the 7-segment display. We are going to be doing this two-sided. I think by default it's two-sided, so you don't have to worry about those settings. If we're doing it one-sided, it's gonna be a little bit difficult in terms of all the connections we have to make. And that question is regards to how many layers the PCB is, I believe. Okay. To place a part, we are going to place the 74LS47 part onto our PCB as the first thing we're going to do. So go to place, go to add symbol, and this will load up all of the symbols and all the symbol libraries that appear on the screen. And you will type in 74LS47. Right? So, onboard markers, you should need my backpack. Okay. So, 74LS47 is one of the 50,000 most common electronic components in the world, I guess. That's why they already have it for you. Now, if the KiCAD library does not have a component, you'll have to go searching for more components in the World Wide Web. So lucky for us, we can go ahead and double click this and place it in our schematic, right? And once we place it in our schematic, we can click cancel. And we'll see something like this. The 74LS47 chip has 4 inputs, 7 outputs, an external VCC and a ground, and 3 pins for control and reset, right? As expected. Now, the brains of our system requires this decoder to translate our 4-bit number into a 7-segment display. We also need a 7-segment display, right? In order to complete this. So we're gonna go to place, we're gonna go to add symbol, and we're gonna type in 7-segment display. Okay, here's where we will differ, because I have this thing called an HDSP7501, but I'm gonna guess that you don't. Am I correct? Okay, you'll notice that this is a custom library that we have to add. So based on whatever you've downloaded, go ahead and go back to the previous KiCAD screen and go to the symbol editor. Now, like I said, by default, I guess the 7-segment display is not one of the 50,000 common components, so they didn't include it by default. So what you have to do is you go to the symbol editor, go to File, go to Add Library, go to Global, press OK, and you're going to go ahead and add the library from your downloads folder, and it's going to be called 4x04-cpph_demo.kicadsim. I'm not going to do this because I already have the library. But hopefully, after you double click this, it'll install itself into your library loader and create a new section called 4x04-cpph_demo on your library manager. Yes. Sure. So in order to add a new library, go to File, go to Add Library, click on Global, and the difference between Global and Project is that if you click Project, the library is only going to appear in your project. But if you click Global, it's going to appear everywhere so that you can use it in other projects. Click OK. You're going to find where your file is that you downloaded. It should have the .kicad_sim extension attached to it. That's the symbol file that KiCAD recognizes. You're going to click Open, and it's going to install itself on the sidebar right here. Yes, this will also be posted later. Oh, also, this was already posted, the files in the Hyperloop Discord, so you can get them there. But we'll post the recording later as well. So once you have this downloaded, you'll notice that a new symbol appears called the HDSP-7501. And if you download this from the website, by the way, the pinouts are wrong. I actually had to manually correct this pinout to be able to support what we're doing today. Oh, you're still downloading? Oh, no worries, no worries. Okay. So, does anyone have this downloaded yet? This symbol downloaded? One person. Okay, I'll give it like 3 minutes. While you're downloading that, I'm gonna go check on another.
I can't see the finding that library option.
Yeah, I have to So go to the main menu, go to the other window, symbol editor. Add library. Okay. And we're gonna find the balance. The balance is okay, where is it? Oh, so make sure you download the .sim file from the Google Drive. It's under the Hyperloop Discord, under General. So it should take you to this folder right here. And this folder has the .KiCAD sim file. This is the symbol, and this is the footprint. Note that the footprint comes inside of the zip file because the extension is called .pretty. Why is that? I have no idea. Yeah, okay. So, the file. Oh, you have to get this. Go click on that. It's not there. Yep. Okay, who does not have it yet? That is the .pretty, right? You have the .sim. Okay, go ahead and download the other one. Go back. Now this one. Add my one. Do you have mine? Oh, it already exists. Okay, scroll to the top of this. Alright, awesome. Okay, looks like we're all on track. So now that we downloaded the symbol, let's kill two birds with one stone and download the footprint for it as well. Because remember, for every component you use, you're going to need a symbol and a footprint. The symbol goes on your schematic, the footprint goes on your PCB schematic, and if optional, you can design a 3D model for it as well, but that's optional. Okay, so exit out of this page and go back to your, I'll call this the home page of your project. Click on Footprint Editor, right? This little IC symbol here. And you are going to do something very similar. If you have the .zip file, remember to unzip it before moving on, okay? Go to File, go to Add, go to Global, click OK. And now you're going to go ahead and find your folder called 4x04_cpph.demo.pretty, right? This .pretty file is where the footprint instructions are stored. Click Select Folder, and then you'll get this on the sidebar. Click on the D1X8K, and you should see something like this. So this just means that you've added the footprint of the 7-segment display into your schematic, or into your PCB schematic. Yes. So from the very beginning, and I'm going to go straight from the home page. From the home page, go to Footprint Editor. When the Footprint Editor loads, you're going to go to File, Add Library, Global, click OK, find your 4x04_cpph.demo.pretty folder, click in it, and then click Select. And that should install itself into your library. And then you go under Item, select D1X8K, and then you should see something like this. We're going to stop here. Give you guys a few minutes. I'm at saying create a project part. Okay. All right. Who does not have it downloaded yet? Okay, to move on. So for the most part, what we did here is pretty much just we install the footprint, which is what you're going to do 90% of the time. Later on, though, we're going to do something called creating a footprint, where we make the part for whatever we want, right? So you can actually make this yourself if you know what part you're going to use. However, if you're lazy like me, you can just Google, 7-second display footprint, download off the internet, and boom, there you go. Okay, you're just lost. Sorry, no worries, no worries. Are you still at the beginning part? So you've created a project, and you just need to install the symbols and the footprints now. Okay. So what we're going to do next is go back to our schematic. And once we're at the schematic, now we can install the footprint that we just created, right? The 7-second display. And now when you type in 7-second display, you'll actually see it appear on the screen. So we see the HDSP-7501. We double click this, place this in our schematic, and we can see now that we have the decoder. We have the decoder and our display in the same document, right? Great. So now we have to make the electrical connections between the decoder and our 7-second display. And it's pretty simple. All we got to do is just click on one of these end terminals and drag the wire over to the display. And you can see that at least for this circuit, we know that we can just make these connections because they relate to each other, right? The outputs of the 74LS47 are the inputs of the 7-second display, right? Okay. Now let's talk about power. Does anyone remember what the output of what the CA pins of the 7-second display should be connected to? CA stands for common anode. Ground or power? So remember, there's two types of 7-second displays, right? One of them is ground and the other one's power. While we think about that, let's go ahead and place our power components. Common anode, yes. 5 volts, yes, hey, we got it. So we need to connect both the CA pins to the 5 volts. So we're gonna go to place, we're gonna add power, And in add power, we're going to go to this drop down menu here and select the 5V or the VCC. Actually, let's do VCC. All right, let's do 5 volts. We select the 5 volts power symbol, right? And we drag it next to our common anode pins. Okay. Does anyone remember what else we need to connect the? Sorry, yes. 5V, the one that says 5V, right here. Yeah. So what was it? We need a resistor, right, for the common anode. So we're actually going to go ahead and go to power again. We want to find a ground, a GND, right? This one right here, I just saw it, yeah. And this will help tell our circuit what the ground is. So double clicking on this and dragging it into our circuit, we're just going to place it where it says ground and then connect the dots. So really all this is a big connect the dots game, but you just got to know what to connect the dots with. I'm also going to copy this 5 volt signal and connect this to the 5 volt pin of the 74LS47. Control C, Control V. Yes. So click on the component, Control C, Control V. All right. So we need a resistor in order to connect the common anode output to the 5 volts. So we go to place, we go to add symbol, we type in resistor, actually just R, and you should see this pop up. This is a generic resistor footprint or symbol. So go ahead and double click this, and you're going to place this on your schematic. Now, this is a generic resistor, but we're going to characterize it by double clicking the R and changing into a 1000 ohm resistor. I'm going to change to 1K. When I press enter, this will change the value into 1K. Yes. To get a resistor, go to place, go to symbol, type in R, and it should be the first thing that pops up. Okay, so both of these pins will go into the resistor, like so, and into 5 volts. This completes this back half of the circuit, right? Now, let's deal with the others. Let's deal with all LT, BI, and RBI first. Does anyone remember what the purpose of these pins are?
All those are flat, it doesn't reset.
Yeah, so it's reset or clear pins, right? So if we feed a 5 volt signal into it, it won't reset or clear. Okay, so we're gonna take our 5 volt signal, we're gonna press R to rotate, and it's gonna rotate into this direction, and we're just gonna connect it to all 3 of these pins here. If you wanna know the purpose of these pins, you can go ahead and look at the data sheets. But you just don't need to remember it, just remember to connect it to 5 volts. Okay, our circuit is almost done. Our first module is almost complete. The next step is to connect our inputs to A, B, C, D, right? But in this scenario, I actually don't know what my inputs are yet. So as a compensation for this, I'm just gonna create 4 wires sticking out from my inputs. And then I'm going to use what are called net labels to complete the dots. So after I place these wires, I'm going to go to place, add label, which is this symbol right here. And then I'm going to type in O1, right? And O1 is going to represent each bit of my input. I'm going to place it on my wire. Now this is pretty important. Each wire is known as a net, or every series of wires is known as a net. This series of wires right here, where it says 5 volts, is known as a 5 volt net. Nets are groups of wires. So if I label this as O1, this net becomes O1, right? If I use this net or this wire and label it O1 anywhere else in the circuit, that anywhere else in the circuit also becomes O1. That sounds confusing, but I'll clarify later. Every single individual wire that represents a connection between 2 points is known as a separate net. Whenever I reference net, that just means a specific group of wires, right? So this right here, at the output of the resistor and before the 5 volts, this is a 5 volt net, right? Which means this point and this point, so for the Zoom guys, the point after the resistor where it goes to 5 volts And where it says LTBI and RBI to the left, these are the same connection, right? In a PCB, I'm gonna have to find a way to connect this point and this point together. You got that? Okay, so me labeling this 01 just means I can reference it later in my circuit. All right, yes. Yes, so go to place, go to label. I'm gonna do O2 as well. And you'll create that and you'll place it on your wire. Now for quickness, I can just go ahead and copy paste this again. I'm gonna make this O3 and O4. Like that. So now I have a complete circuit, right? I've labeled my inputs from O1 to O4, representing the 4 bits. I connected my LTBI RBI to 5 volts to prevent reset and clear. I've connected the external power to the chip and the outputs of the chip to the inputs of the 7-second display. So this whole thing is my decoder circuit. A lot of times with circuits, you'll have multiple components that are working together simultaneously to create a certain goal. To represent these components nicely, you want to create a text label, right? You want to label your circuits. So press T, and you'll be able to create a text box. I'm going to call this my decoder circuit. I'm going to make my text size 1.75, and boom, decoder circuit. All right. So we are 1 out of 4 circuits done with creating this schematic. Does anyone remember what the next circuit is? User input, that is correct. So we need a way for the user to be able to interface with the circuit, right? So does anyone know what parts we need for this circuit? A switch, right? Now the type of switch we're going to use is known as an SPDT switch. Does anyone remember what SPDT stands for? Whoa.
Single pole. Single pole.
Yes, single pole double throw, right? There's 1 inputs and 2 outputs. So this is also known as a 3-terminal switch, right? A switch with 3 terminals. So what we're going to do here is we're going to take 1 switch and copy it 4 times because there's 4 bits for the input. So I can just copy it once and then copy it twice. Lightning fast, all right? Now, at the start of the switch, we're going to connect everything to a high signal, right? And when the user switches the switch on, it's going to give that high signal down to the circuit. So in this case, a high signal would represent what? Someone say 5 volts? Yeah, 5 volts. Okay, so we're going to connect the 5 volts to the single pole part of the circuit. So we're going to connect this to all 4 of the beginnings of the circuit, like this. Okay. All right. So the next part is I'm going to make a huge line here. And then I'm going to connect the other side of the switch to my outputs, right? So again, I can just go back to my other circuit, copy this part, and paste it here. This is O1, and I have O2, O3, and O4. O3, O4. Like this. Okay, is my circuit done?
No.
What do I need?
Ground.
Oh, we need a ground somewhere, but
Just pull down the
we need a pull down resistor. Good. And the reason for a pull down resistor?
give it on the ground. Zero.
To, yes, basically to give the circuit signal a 0 point. My phone go? I seem to have lost my phone, but it's okay because we're gonna put a pull down resistor. So we're gonna take a resistor and we're gonna put it on the bottom of the circuit. Now, a thing about circuit schematics is that you often want to make it neat, right? So what we're gonna do is we're gonna make our circuit neat by putting the resistors down at the bottom. But we know that the pull down resistor must come from every line of the switch outputs. just to make sure there's no floating points, right? There's no floating outputs. And then what goes at the end of these resistors? Yep, you guessed it. It's ground. Okay. And for the last thing of the circuit, we're going to need something called a no connect, right? Because what goes on the other side of the switch? Nothing. So to put a no connect and to let the electricians know that there's not supposed to be anything that goes there, you hover over a terminal and press Q, and the Q places an X on the end of the switch. This clarifies it because it, signifies that you didn't forget that there's nothing there, but you know there's nothing there. So you're telling other people that there's nothing there, right? And the circuit is known as our user input circuit. Okay. I'll give you some time to finish that while I go look for my code. Right. So you need to catch up.
Yeah, and mustard.
What?
Said and mustard.
Oh, haha, you get it. Okay, awesome. All right. Seems like you guys are getting the hang of the fundamentals pretty well. So let us continue. What happened? So the X symbolizes a no connect that tells other people that you know there's nothing there. Some people may think that if you don't put this, you might have not finished circuit yet. So hover over this and press Q. That puts a no connect there. You can also go to place and do it from the UI. Add no connect flag. It's just a shortcut, Okay. Now, does anyone remember what's going on next? What's next? The third circuit. Yes, it's the LEDs. It's the user validation circuit, right? So we just connect an LED or series of LEDs to the output of 01, 02, 03, 04. Now, I preliminarily copied and pasted the LED circuit outwards because I know each LED is going to need a resistor, right? So I'm going to go to place, add symbol, and let's go ahead and find our LED symbol. We see our LED symbol right here, and we're going to go ahead and place it on our circuit, like so. Okay, then we can copy paste this 4 times. And connect the dots. Okay, thought question. What goes at the start of our LEDs? What turns these LEDs on?
Power?
Power turns LEDs on, but exactly what type of power? Be a little more specific. Yes, the user, right? 01, 02, 03, 04. Good job. 02, 03, 04. Okay. Alrighty. And I'm just going to name this as my user validation circuit. Making the user feel comfortable about what they're doing. All right, so we have 3 circuits so far. Our decoder circuit, our user input circuit, and our user validation circuit. What's our 4th circuit? Yes, power regulation. We need a way to give our circuit the power it deserves, right? All right. Now, in theory, we're going to connect a 9-volt battery to this circuit. And 9 volts is too high, so what chip do we need to regulate it down? Yes, we need a voltage regulator. A specific chip is called the AMS1117, and we are going to use the fixed voltage regulator of 5 volts. This chip right here. Double click that and put that into our circuit. I'll put it down here. This one's going to be quite the biggie. So we'll work from here. All right. So in this circuit, we know that we're going to pass in a 9-volt signal, right? We're going to get a 5-volt signal out. And this terminal just goes to ground. So we're going to very quickly put everything in place. Ground goes to ground. We have our 5 volts that goes on the right side. And on the left side, we're going to go to place, add power, and we're going to find a 9-volt power terminal like this. And from the 9-volt power terminal, we're going to place this on the left. Okay. Now, in theory, this circuit will work, right? You're going to have 9 volts going in, 5 volts going out, and ground to ground. But in realistic times, this won't work. And why is that? What are we missing? The caps, the capacitors. Yeah. Oh, did you say something else?
Yeah, cathodes.
Oh, close enough. We're going to have caps there, right? So capacitors. So capacitors in KiCAD, you can just represent them as C, unpolarized capacitor. And we're just going to put them, you're going to copy and paste them, 4 of them. 1, 2, 3, 4. And connect them to our power rails. Now, when you get into PCB design, you'll start calling things by what the industry calls them. And anytime you have like a power or like a line that supplies power, we call those power rails. Anytime you have a line that supplies logic or data, you call them data rails. It's very cool terminology. Okay. So I'm going to rename these capacitors to their actual values. This one's going to be 10 microfarad. This one's going to be 0.1 microfarad. Remember, 10 microfarad for big signal, 0.1 microfarad for small signal. .1 microfarad for a small signal. Yay! Okay. What's next? We have our regulator circuit. We have a way to give 9 volts in our circuit and get 5 volts back out. What's next?
You need some sort of protection.
Sure, let's do protection first. So we're going to add a diode. We're going to place, and this diode is called 4001. And this is going to be under diode. Don't get tricked out by the quad NOR 2 inputs. Under diode, we have the 1N4001, which is the 50 volt 1 amp general purpose rectifier diode. Double click this and then rotate. We're going to put this between our 9 volts and the rest of the circuit, right? Delete this signal, put this diode in, and then put it in combination with the circuit. So great. We now have a diode. Our circuit will be protected from dummies like me who want to stress test your circuit by connecting the battery backwards. What's next?
We need some sort of LED to let us know if the circuit is on, turned on.
Good, user validation. I want to know when my circuit turns on, so I'm just going to copy this LED circuit from here and rotate it and place it down. As easy as that. Good. My user is validated. I know when my circuit is getting power because my LED tells me so. And my circuit is protected by this diode. What's next? What other utility features can we use? So when I have the circuit in my hands, right, I want to be able to use it whenever, and I want
Or
to,
switch
yeah, switch. I want to be able to turn it off whenever I want.
between the 9-volt and the diode.
Exactly, yes, that is correct. I'm gonna copy my switch here, and I'm gonna put it between my 9 volts signal and the diode, because when I get the circuit in my hands, I want to be able to turn it on and off whenever I please. Okay, the last thing we're gonna do is put a terminal block connection, because physically, you're gonna need a way to connect your 9-volt battery to the circuit. And the most obvious way to do this is by using a terminal block connector. We're gonna go ahead and type in terminal block. The screw terminal 01x02 is what we're gonna be using. And we're gonna place it on our circuit like this. I'm gonna press the X button to flip it, because my 1 is gonna go into power, 2 is gonna go into ground, and this is going to go into the rest of my circuit like this. And my 9-volt power point is gonna go in right here. I'm gonna put my ground at the other end. And that completes my power regulation circuit. Okay. These are the circuits we've designed so far. And I'd like to point something out. This is not one circuit connected all together, right? It's like 4 separate modules. But the thing you have to understand is that it's all connected together. Wherever it says O1, O2, O3, O4, you can think of that as portals, right? These signals exit through these portals here, but appear anywhere else in the circuit. So remember that this O1 is the same as this O1 in the user validation circuit. It's also the same O1 as in the decoder circuit. So when you're wiring this together, you say, like in your mind, think, okay, these are going to be all connected together with the same wire, right? In the schematic, we're just putting them all apart because, you know, it looks neater. It's easier to analyze each individual module by itself rather than to have everything in one big jumbled mess. It's especially important when you work with microcontrollers because those have a lot of input and outputs. And it's easier if you just use net labels to organize your work. Okay. Does anyone have any questions?
How did you change the value of the capacitors?
So I just double clicked on here, it opened the value field menu, and I just changed the name.
Even another question.
Yeah.
Where are the capacitors again?
Oh, so go to place, go to add symbol, and press C. See the first thing that pops up. Yeah, capitals. Doesn't even matter. Okay. The next part is pretty fun. The next part is called footprint assignment. Okay. Now remember that these are only symbols. They don't represent the actual components themselves or what they actually look like. We need to represent that using a footprint. So if we go up here and we go to the Run Footprint Assignment tool and click on it, we can see that brings up a whole menu of different things. So what we're going to do is we are going to assign footprints for each of these components. And I don't have a list of what these things are, so I'm going to look in a previous project of mine. We're going to copy it from there. I did a practice run of this earlier. Okay. Here we go. These are the footprints you're going to assign to each component. Because remember, each component needs a picture of what it looks like on the actual PCB. It can't just, do it based on the symbol. So the first thing is going to be these. Let's do all the resistors first, because completing things really quickly is pretty satisfying. So resistors are going to use this footprint, right? Looks like a really long name, but here's how you search for them. You scroll down to the library where it says resistor _ THT. Does anyone remember what THT stands for? Yeah. Stands for through hole component, right? So components that go all the way through the PCB. We're going to search up Pretty much, this has footprints of all different shapes and sizes. And when you design your own PCB, you'll probably be looking at this for hours, thinking of like which size your component is. Lucky for you, I already know which it is. So we're gonna do L 3.6 millimeters for the resistor, underscore D 1.6 millimeters, underscore P 7.62. Okay. Yeah. So you're going to go to footprint assignment tool in the top right corner here, and there's this little button there that says run footprint assignment tool. Okay. L stands for length, D stands for diameter, P stands for pitch. So double click this, and you're going to assign these to every single one of the resistors we're using. This is the most accurate resistor size for a 1/4 watt resistor. The wattage of a resistor tells you how much power you can stuff through it before it blows up. So a 1/4 watt means 0.25 amps. 1/2 watt means 0.5 amps. 1 watt is 1 amp. Sorry, not amp. Watt is power, so it's like amp times voltage. Ignore everything I said. It's the amount of current you have passing the resistor times the voltage. Okay. You'll see that some components are actually assigned for you already, like this diode here. But unfortunately, KiCAD is stupid because this diode footprint is wrong. It's a little bit too big. So we're going to go to diode underscore THT, and we're going to find the correct one. It's going to be the 7.62 millimeter horizontal footprint. And an interesting fact, you can actually see what these footprints look like if you press this magnifying glass right here in the menu. It says view the selected footprint in the footprint viewer. So I'm going to click that, and we're going to see what it looks like, right? Ooh, very pretty. When you're searching for footprints, usually you can use that tool as a helpful guide. So we're going to change the diode to a 7.62 millimeter. And keep going. You'll see that some components already have assigned parts to them, and these are the correct ones. You don't have to worry about them. Okay, let's go to 74LS47. This component requires a package underscore DIP parts, right? DIP stands for dual inline package. So package underscore DIP is going to be under here where it says package underscore DIP. And we're going to use the one that's DIP-16. So DIP-16, I believe it's underscore 7.62 millimeters. This exact package right here. Okay. Next, we're going to go to screw terminal. For the screw terminal, we need to get the, let's see where it is on mine. Seems like it doesn't exist on mine for some reason. Oh no, it's right here. Okay. So the screw terminal, we're going to go to terminal block right here. And we're going to get the Bornier-2 footprint, P 5.08 millimeters. So go to terminal block underscore Bornier-2. Bornier is a funny word. Okay, next let's take care of the LEDs. The LEDs that we're going to be using come in this size. So we go to LED underscore THT in the footprint menu, and find the one that says LED underscore D 5.0 millimeters, which would be this one. And then you can go ahead and double click it and assign it to each of the footprints that require an LED. Okay, let's go to capacitors. We have 4 capacitors on our PCB. For the 10 microfarad capacitors, I'm going to use these as my electrolytic capacitors. There are different kinds of capacitors. You know, electrolytic, in it, it's called radial. So go to capacitor underscore THT, and you're going to type in radial underscore D 4.0 millimeters underscore H 7.0 millimeters underscore P 1.5. And this is the one we're going to use. Okay. For the 0.1 microfarad capacitor, smaller capacitors usually come in the form of ceramic capacitors. So we're going to do capacitor underscore THT. Actually, no. We're going to do disk underscore D 5.0 millimeters. And then we're going to find the one that's 2.5 millimeters in pitch. This one right here. Okay, so now we've assigned the capacitor footprints, right? And everything is pretty much clear except for the switches. Fun fact, the switches we're going to be using, the 5 millimeter slide switches, they don't actually have a footprint for that because it's not a common part you solder onto a PCB. So in order for us to actually have this PCB, we have to make one. Now, unfortunately for us, we don't have the time to make one, but I can go over really quickly how to make one in general. Let me go ahead and just check that I have everything. Okay, right. So to make a footprint, what you're going to do is you're going to go into the home menu, go to footprint editor, and you are going to go to your CPPH demo folder, and you're going to go ahead and click create new empty footprint. You're going to name this slide switch underscore 5.0 millimeters. And you're going to make this a THT, a through hole. Press OK, and it's going to give you an empty footprint, right? We're going to go over how to actually make one of these, which is fun. You're going to take a pad, you're going to put the pad down, and you're going to change the pad dimensions. And this pad is going to have the dimensions of, and actually I don't know this, I have to go ahead and check. Custom components. Okay, hold on. I'm going to go check on my practice run PCB to see what the dimensions of this is. Okay, so we're making these switches right here. If I check the dimensions of this pad, the diameter is 0.125 inches and the diameter of the hole is 0.075. So I'll go back to here and say, okay, I want a 0.125. Actually, it's in millimeters. I don't know why it changed, so inches to millimeters. 0.075, 1.905 millimeters for the circular hole, and the pad shape is 0.125. 3.175 millimeters. If you have it in inches, it's going to be a little bit different. But so have your dimensions of your pad like this, press OK, and then just copy this 3 times. And you're going to place this about 5 millimeters across from each other. Right? I believe my grid is snapped like that. Okay. Now we have to label the pads because the switch has different pads and each pad is corresponding to a terminal on the symbol. So in our pad here, we have the symbols 1, 2, 3 from left to right. So we're going to go ahead and go to the pad symbol and create this and change this to 1, 2, and 3. Like so. Okay. These pads, remember from the lecture, are places where we can put our components through, right? They're spaced this way such that it's easier for us to do so. The next thing we're going to do is create an outline for the switch. So you're going to go to the front cell screen, grab your line tool, and you're going to create a box around this switch. Kind of like this. Make the box a little smaller. And this just signifies, where your switch is on the PCB. Everything's separated into little boxes. Once you have this box and once you're done with the positioning, you can go ahead and press Control S and you can save it inside your demo library, like so. So now in your demo library, you'll have the footprint of your 7-segment display and your slide switch. Once you have that, you can return to your schematic. Okay. Click on the footprint editor once more to enter the footprint assignment. and go down to the place where it says switch 1, switch underscore SPST. You're going to go ahead and click on your library, your custom library, and you are going to find your switch, your slide switch footprints, right? And you're going to assign them to all your switches, like so. Apply, save schematic, and continue. All right. Once you have your assigned footprints, you are going to go ahead and place it on your PCB schematic. All right. Press F8, and this will generate all your components onto the PCB. Press Update PCB, close, and you will see that all of your components are now resting on this PCB schematic right here, right? Okay. So at this point, we are almost done with our PCB design. But you know, this is actually the hardest part of it all, because you kind of got to stare at this for a long time and figure out exactly where everything goes. And this takes a long time, trust me. Like the perfectionist I am, I always spend a lot of time doing this. But if you press Control-3 at this point, you'll be able to see that your components are almost all on the PCB. They're just like in really random orders, right? Or like the automatically generated orders. You might have a lot of fun with this, or you might hate this part very much, but then you have to place every single part in the correct spots. And you know, this takes hours on end. PCB design is not a quick process. It usually takes me anywhere between 1 day to 2 weeks to create a PCB design from scratch. And that's with already having the circuit. Sometimes you don't have the circuit at all. And we have 7 minutes. So what I'm gonna do is I'm gonna go ahead and breeze through this really quickly. Assuming that I already have all my PCB designs intact, you can go to the grid and you select a grid snap margin like this in order to get what you want. Grid snap is really cool because it allows you to just snap the parts together. And it's a really quick way of doing so. Usually what I start with is I format these switches. So I take all the switches out of their corners right here, and I put all the switches together, right? When you're designing a PCB, it's very similar to like designing the schematic. You want every module as close together as possible so that you don't have any confusions. You'll notice that this switch is in charge of the power. So I want all my power components together, right? So my power components include this switch right here. I have my terminal block right here. And I have my regulator module right here. All right. Then I can put my capacitors with it as well, like so. And I can leave it there for now because all of these components make up power, right? Now, all these switches that are clumped together in this section, these make up the user input, right? The user is going to use these switches to select their stuff in general. So you want them to be all in one section. You also want the pull down resistors to be in the same section as well, so that later on you can align them together. Again, because I'm rushing through this, alignment's not gonna be pretty, but you can use this button to open it in schematic editor and get these numbers of the resistors you're gonna use. So I can see here, I'm gonna use R2 to R5 in the user input. So R2 to R5. Drag this out and plop this with the user input. Next is the LEDs, right? User input LEDs is going to be from R6 to R9, I believe. R6 to R9, you can see that selected. And D1 to D4. Just going to clump them together like so. All right. Next is my circuit that controls a 7-segment display. I'm going to have my display, my chip, and the resistor that goes along with it right here. Right, and this 1K ohm symbol is going to go with it. Right. All right. Actually, it's R1 that goes along with it. You'll see that a lot of these lines that are spanning across my schematic are just because these are the rat's nest, right? We talked about. The rat's nest showcase where I need to place my wires to connect all the components together. This diode goes to my power circuit as well. I'm gonna plop it right here. And this LED is my power LED. So of course this goes with that as well. Okay. The purpose of me showing you this is that I can clearly see all 4 of my modules put together, right? And then I can organize the PCB with that in mind. We have 3 minutes left. We didn't get to wiring and routing. Again, PCB design is a long and arduous process, but I will show you what it looks like at the very end once you have routed everything and put them into a schematic together. So I'm going to show you a practice run. A few days ago on my Twitch stream, I built this PCB in practice for this workshop, and the recording has been saved. So if you want to watch me wire this together for about 2 hours, I will post this onto the Hyperloop Discord for your viewing pleasure. But you'll see how the resulting PCB has all of the individual modules lined up together, right? We have the switches, we have the LEDs, with pull-down resistors, power regulation module on the right, with all the LEDs and diodes, the 7-segment display, and it's all collected together in a nice pipe. There's a lot of theory behind connecting the wires together. For example, again, remember how we said that current is really important in connecting the dots? The width of this trace is within IPC standards. If you want to Google that term later, please do so. It's like a standard for PCB design. It states pretty much how thick your traces have to be depending on how much current you pass through your circuit. This is a 15 mil trace. Mil stands for thousandths of an inch. You don't want to confuse that with mm, because mm stands for milliliters, but MIL stands for millionth of thousandths of an inch. It's not millionth of an inch, it's thousandth of an inch. It's weird. It's like one of the conundrums of PCB design. You get us confused. Anyways, I'm assuming here that the maximum, and I'm being really conservative, current in my circuit is going to be 1 amp, right? Behind the 1 amp is 1 amp. So these are 15 mil traces, right? So in this scenario, once you've connected all the dots together, then you can go ahead and just add your silkscreen. All the white lines and white traces on this PCB are known as silkscreen components, and you can add cool things like your own logo to it, right? So if you want to add a name, your company, your favorite vegetable onto the PCB afterwards, you can use. But in general, the whole design process I've streamed onto my Twitch bot. It'll be posted in Hyperloop, so you can watch that all 2 hours of it. And in the bot, I also talk about pretty much all the other PCB design concepts. So you can go ahead and do it yourself. Before I conclude, are there any questions? We have classes for this, so like doing all of this in 2 hours is already really impressive. But again, post-workshop activity, if you like to design your own PCB, get it ordered. And you can solder it during the soldering workshop. If you have common components on your PCB, we'll get the components to you too, so you can make it your own. But in 2 weeks' time, I'll put the nitty-gritty details on Discord. You can submit a Gerber file, and actually, let's go over that really quickly on how to do this. So if you Google JLC PCB, KiCAD, Gerber file, a Gerber file is the file format in which fabrication companies accept, like Chinese fabrication companies. They use that to make your PCB. So it's a bunch of instructions put together on how to drill and design your PCB. So this website will be posted afterwards in order to get your PCB from the design into a file. And so you will submit me or any other Hyperloop eBoard member a .zip of your PCB's Gerber file. We don't want your project file, we want a Gerber file. And then we can get it ordered for you free of charge. Your PCB's on us. All right? Okay. So if there's no more questions, then this workshop has officially concluded. Thank you so much for coming today and spending your Friday night with us. Hope you guys learned a lot, and I hope to see you guys in future workshops. Thank you.